Hi everyone, welcome back. Today I'm going to solve a question. It's a simple two-period consumption model. We want to maximize utility from consumption in the first period and consumption in the second period, and the second period consumption, the utility that you get from that is being discounted. Okay, we have two budget constraints. The first is that the income in the first period must equal the consumption in that period, and also the amount that you put as in investments in assets. So your income goes into saving and also goes into current consumption. In the next period, your income is what you earn and also the interest rate that you will gain from the amount that you saved, and this is your disposable income in the second period, and you can use this to fund your consumption in the second period. Okay, so this is we have two equality constraints. So let's start by forming the Lagrangian. L will be a function of C1, C2, A1, lambda 1, lambda 2. Okay, so we want to maximize this. This is the objective function subject to two constraints. The first is lambda 1 y1 minus c1 minus a1 plus lambda 2 and this is the second one minus c2, obviously. Yeah. Okay, so we want to take the derivative of L with respect to first C1 and put it equals to a 0. We'll have, suppose the utility function is given as this. This is the utility function that actually Sir gave in the article that he shared. You can also try this question for another utility function. Let's say utility depending on C is LNC. Yeah, you can try that one as well. It's going to give you the same Euler's equation. Okay, so the derivative of u with respect to C1 is just C1 alpha minus 1 minus lambda 1 is equals to a 0, because there's no C1 here, there is a C1 here, there is no C1 here. Okay, so the first equation is lambda 1 is equals to C1 alpha minus 1, and suppose alpha is a 0.5, then we have a C1 minus a half here. So this is equation 1. Equation 2 is the derivative of L with respect to C2, and we put it equals to a 0. There's no C2 here, there is a C2 here. So 1 over a 1 plus the discount factor, which is rho. This is the rate of time preference, and the derivative with respect to C2 is just going to be this. Okay, plus there's no C2 in this expression, there is a C2 here. So we have a minus lambda 2 is equals to a 0. Okay, moving on. Therefore, C2 over, let's actually first make lambda the subject, and now I can suppose that alpha is equals to half, so we have a minus half over a 1 plus rho, and this is equation 2. Okay, moving on to equation 3, the derivative of L with respect to A1 and putting it equals to a 0. A1 doesn't come here, it only comes over here. So we have a minus lambda 1 plus 1 plus r into lambda 2 is equals to 0. So we have a minus lambda 1 plus lambda 2 1 plus r equals to 0. Let's just have all positive constant coefficients. This is my equation 3. Okay, the next are just the constraint themselves. So when I take the derivative of L with respect to lambda 1 and I put it equals to a 0, and I take the derivative of L with respect to lambda 2 and put it equals to 0, I'm just going to get my constraints back. So these are going to be my equations number 4, and this is going to be my equation 5. Okay, so now we have all we need to solve our question. First, let's look at the budget constraints. So remember, this is the budget constraint, so and this is the budget constraint. So combining these two should give me the intertemporal budget constraint. So from equation 4 and 5, because these are the budget constraints, we can obtain the intertemporal budget constraint. Okay, so in 4, if I make a1 the subject, I have a y1 minus c1, and from equation 5 I'll have a c2 minus y2 over a 1 plus r. Okay, so therefore I'll have y1 1 plus r minus c1 1 plus r is equals to c2 minus y2. What we can do over here is keep consumption on one side and keep income on the other side, and it's better to write it as a present value of consumption, lifetime consumption, and present value of lifetime income. So I've just divided through by 1 plus 4. So this is my equation 6, and it's known as the intertemporal budget constraint. Okay, now what? We need to find the optimal consumption and optimal current and future consumption, right? So from equation 3, we can see that lambda 2 1 plus r is equals to a lambda 1, and we can now substitute 1 and 2 into this, right? So lambda 1 was a c1 minus half, and lambda 2 was a c2 minus half over 1 plus rho. Okay, so you can either make c1 the subject or c2 the subject, it actually doesn't matter. So 1 plus r over c2 power half 1 plus rho is equals to 1 over c1 power half, and therefore a c2 power half is going to be equals to 1 plus r over a 1 plus rho into c1 power half. I've just cross multiplied. Okay, so therefore c2 is going to be 1 plus r 1 plus rho square and c1. So now we have c2 in terms of c1. So what we are going to do is that we are going to put this into the intertemporal budget constraint. So just put this tangency condition into the intertemporal budget constraint given by the equation 6. So we're going to put this in equation 6. Okay, this was equation 6, and I'm just going to put this here. So I have a C1 plus 1 plus R square over a 1 plus rho into this. Oh no, actually I did already put it on, and let me fix this. We have a 1 over a 1 plus R into C2, so this is C2, and this is the present value of lifetime income. R plus 1 cancelled out, so we have C1 plus R 1 plus R and plus 1 plus rho square. C1 is equals to y1 plus y2 over a 1 plus R. If I take C1, make C1 the subject, I'll have a 1 plus this expression. And then I can just take this, make a common denominator, and then make C1 the subject, and that's going to be my optimal consumption in the first time period. So here we go, over a 1 plus rho square, and the present value of lifetime income remains here, and therefore my optimal consumption in the current time period is as follows, being multiplied by the present value of lifetime income. Now that we have C1 completely in terms of Y1, we can find the optimal value of C2 as well, which was this. We only need to substitute the optimal value of C1 into this expression in order to find the optimal value of C2. So we have 1 plus R square over 1 plus rho square into this, and the 1 plus rho square actually will get cancelled out, so this gets eliminated, and I have an expression similar to this one, but this time in the numerator I have the following expression. As you can see, that the only difference between C1, the optimal value of C1 and C2 is by this coefficient right here, this variable right here. So whenever R is equals to rho, these are going to be equals to each other. So C1, he's going to be doing consumption soothing. And whenever R is greater than rho, then he's going to become a lender, because the market is offering much more to forgo current consumption than he required. And whenever R is less than rho, then C2 is going to be less than C1 star. So this was the first thing in the PDF sir shared. The next thing I'll be covering is going to be the Bellman equation, but I'll make a separate video for that, so each video isn't that long. I hope this helped, and I'll see you in the next lesson. Take care.